The Fourier relations refer to two key identities involving the Fourier transform. The first statement in the Fourier relations is just the definition of the Fourier transform, which I've remembered here. So the Fourier transform is an integral transform which takes your function of t, evaluates this integral, and ends up with a function of omega we denote with capital F. So that's the Fourier transform, and I'm going to fill in a minute here the second of the Fourier relations. These are really fundamental properties we'll see in a second. So the first thing I want to do is write down the Fourier series for my function little f on the interval from negative L to L. So the complex form of the Fourier series So the Fourier series for my function f on the interval from negative L to L is f of t is equal to the integral from, the sum from negative infinity to infinity of some constant times an exponential function. And that constant is 1 over 2L, the integral from negative L to L of my function f of t times e to the negative in pi over L t dt. And that is a constant after you integrate the t that you multiply by e to the in pi over L t. This is an equality in the interval from negative L to L. Now I'm going to try to take this coefficient in the Fourier series and make it look like the Fourier transform. You could see that they're already kind of close to one another, and in our first video where we introduced the Fourier transform, we saw the connection. So what I'm going to do is I'm going to do two things. Well, first I'm going to say that a new variable omega will be pi over L. See, I have pi over L here and pi over L here. I'd like to let omega denote that expression. So omega has to be some positive number, and I'm going to assume for the moment that my function f of t is 0 off of the interval from negative L to L. So if I'm not in between negative L to L, I'm just going to say that my function f is 0. So I'm focusing on the interval from negative L to L. So then I will get the sum, n going from negative infinity to infinity, 1 over 2L, if I let omega be pi over L, that can be turned into omega over 2 pi. If my function is 0 off of the interval from negative L to L, then instead of going from negative L to L, I can integrate from negative infinity to infinity. It doesn't matter because my function's 0 off of that interval anyway. So I get f of t. This will become e to the negative in omega t. So there's my new expression for my coefficient. And then this will become e to the in omega t. Now I've really got an expression that's close to the definition of the Fourier transform. So this is the sum, n going from negative infinity to infinity. You could see that the integral and the 1 over 2 pi can combine and get f of n omega. I have an n omega instead of an omega. This will be e to the in omega t, and I still have an extra omega floating around. So this is good on the interval from negative L to L. Maybe if I take the limit as L goes to infinity, I'll get an equals for all t. If I take the limit as L goes to infinity, then what happens to omega? Well, omega goes to 0. So What I'm going to do next is I'm going to take the limit as L goes to infinity. Then we see that omega, which is pi over L, has to go to 0. Furthermore, maybe I should draw a number line here. Think about what's going to happen to n omega. So if I have a number line, omega is some positive number. So here's 0 on the number line. Here's omega, 2 omega. I'm going to get n omega for any value n that's an integer. I'm going to have negative values as well, so negative omega, negative 2 omega, and so on. So as omega goes to 0, the tick marks on my number line get closer and closer together. Since I have all values of n going from negative infinity to infinity, as omega gets closer and closer to 0, I'm actually going to get all real numbers. I'm going to get the entire real number line. All the tick marks are squeezed together, and I'm actually going to fill out the entire line. That means omega is going to 0, and omega is filling in every possible value of omega. I actually find the Riemann integral. If I find the Riemann integral, and as L goes to infinity, this assumption isn't such a big deal after all. My function is 0 off of the interval from negative L to L. That keeps getting enlarged. So what I find is my function f of t is the integral from negative infinity to infinity of f of omega e to the I omega t d omega. So this omega became like a d omega because omega went to 0, and the n omega became any value you'd like on the number line, omega. So this is the second of the two equations which give me the Fourier relations. So I'm going to put it in my box here. This was what I was working towards. So the relation is f of t is equal to the integral from negative infinity to infinity of the Fourier transform f of omega times e to the I omega t d omega. So these two combine, that's the Fourier relations. Now, let's do one brief example to illustrate what I'm saying here. So how about if I let the function f of t be a unit step function at 0 times e to the negative t. So it's 0 until I get to 0, and then after that, it's exponential decay. So let's actually calculate the Fourier transform. The Fourier transform is 1 over 2 pi, and then I have to integrate from negative infinity to infinity, but since I start at time t equals 0 with a non-zero function, this will actually just be the integral from 0 to infinity of the function e to the negative t times e to the negative I omega t dt. Now you can evaluate this integral a number of different ways. It's actually a pretty routine integral, or you could even notice that this is 1 over 2 pi times the Laplace transform of this function, where you take the s and replace it with I omega. Or you could just evaluate explicitly, and we get 1 over 2 pi I omega plus 1. So that's the Fourier transform. So the second of the Fourier relations says, therefore, we know that the unit step function times e to the negative t is actually equal to the integral from negative infinity to infinity of this function times e to the positive I omega t. So e to the positive I omega t divided by 2 pi I omega plus 1 d omega. This is a more complicated integral to evaluate. In fact, it's kind of tricky to evaluate explicitly, but I did want to write down an example to show you what the Fourier relations say. The Fourier relations are these two pairs of identities. Now, the Fourier relations are key in understanding the Fourier transform. However, I should remark at this point, because if you go on from this course and use the Fourier transform in other contexts, I should point out that there are alternative definitions of the Fourier transform. So if you look up the Fourier transform online, you'll see different definitions in different places. So let me clarify what those definitions are. You see I have a 1 over 2 pi in the definition of the Fourier transform. Well, some people put the 1 over 2 pi on the second Fourier relation. They put the 1 over 2 pi on this expression, on expression 2 instead of expression 1, and they define the Fourier transform to be this without the 1 over 2 pi. That's fine. Some people don't like to have a 1 over 2 pi in one of these relations and not the other. So some people split the difference and put the square root of 1 over 2 pi in both. So this would be the square root of 1 over 2 pi in f and 1 over the square root of 2 pi in the second. And the last alternative definition I'll actually write down here on the bottom, because you'll see this when you apply Fourier transforms to signal processing and signal analysis oftentimes. So an alternative form would be to write the Fourier transform, my first of the Fourier relations, as equal to the integral from negative infinity to infinity of the function f of t times e to the negative 2 pi I omega t dt. And the second of this alternative form of the Fourier relation would be your function f of t is the integral from negative infinity to infinity of the Fourier transform f of omega times e to the positive 2 pi I omega t dt. And the way that they got this expression, it looks like there's no 1 over 2 pi term, but they got this alternative form from doing a u substitution in the original Fourier transform. They did the substitution like omega got turned into 2 pi omega. And if you just follow through the details, after you do the u substitution, the 1 over 2 pi term goes away. So there are different definitions of the Fourier transform, but they all hinge upon the basic Fourier relations. And in this course, we're going to use the definition I gave previously. All right, excellent.